let's talk about goodness of fit tests. We've talked about M&Ms before in this class. Suppose that the M&Ms company claims that 20% of its M&Ms are orange, 13% are red, 14% are yellow, 16% are green, 24% are blue, and 14% are brown. Suppose we wanted to test this claim to see if these percentages were accurate. How would we go about doing that? We would collect a random sample of M&Ms, and we would count the number of each color and see if their proportions or percentages corresponded in that sample to this claimed percentage from the company. We would need, of course, to have a random sample, and it would need to be sufficiently large in order to test this claim. Really, we're kind of testing 6 claims embedded within this one statement. Each color is a claim: 20% orange, 13% red, 14% yellow, etc. So when we do this hypothesis test, we want to see if these observed numbers, so the number of each color that we count in our sample, is close enough or matches enough or fits to or conforms to the percentages given by the company. So in this test, we are comparing our observed data values from our expected data values, or another way of saying it would be to compare our observed percentages to our expected percentages. The percentages that you're looking at now on your screen are the expected percentages. We've just described what's called a goodness of fit test. A goodness of fit test is a hypothesis test used to determine whether observed data values fit or conform to an expected or claimed distribution. Let's go through the components and notation necessary in order to perform a goodness of fit test. So first of all, we mentioned we need to have observed values and expected values. O, or capital O, stands for the observed values. These are what we collect. This is our sample of M&Ms. These are going to be counts, so they will be whole numbers. For example, say that our observed sample of M&Ms has 15 red M&Ms and 7 yellow M&Ms. Those would be observed values. The expected values come from the probabilities given in the claim or the implied distribution. So if we have 100 M&Ms and we know 24% of them should be blue, we would expect 24 of our 100 M&Ms to be blue. That would be an expected value. It's not what we observed, it's what we expect to get in any random sample. K represents the number of categories. So in our M&Ms example, K is 6 because we have 6 different colored M&Ms. After you've come up with your claim and found your observed values and calculated your expected values, it's time to write down your hypotheses. In a goodness of fit test, your null and alternative hypothesis will always be the same. The null hypothesis is a good fit. So with our M&Ms example, a good fit, or the null hypothesis, would mean that the observed values match or conform to the expected values. The alternative hypothesis will always be not a good fit. If you are supporting the alternative hypothesis, it means that your observed values do not fit or they do not conform to the expected values or the expected percentages. It might be possible in the alternative hypothesis for some of your observed values to fit the claimed values, but if you're supporting the alternative hypothesis, it means that at least one of those values differs significantly from the claim. So even if some of them work, like maybe we have the right number of yellows and the right number of orange M&Ms, if we don't have the right number of reds, that's enough evidence for us to reject the null hypothesis and say that the data is not a good fit. After we have articulated the hypotheses, it's time to use our data to calculate the test statistic. The test statistic uses the new distribution the chi-square distribution. So our test statistic is a chi-square variable. In the past, for hypotheses, we've used either the normal distribution or the student t distribution. So our test stat was either a z or a t. Now our test stat is going to be a chi, which kind of looks like an x, but it's the chi-square. So it's like this curly x. The curly x is the Greek letter chi, and then it's a square because of actually the way you calculate it. So here's how you calculate it. Remember, we're measuring the difference between our O's and E's, between our observed and our expected values. Now, if we find the difference of each O and E in our data, so for M&M's colors, we're saying how many reds did we get versus how many reds do we expect, how many oranges did we get versus how many oranges do we expect, we are going to take the difference in the observed and the expecteds. But when we do that, we could end up with positive and negative numbers. And then when we add them all together, they actually end up canceling each other out. We actually discussed this with the standard deviation. The same thing happened. These differences, these deviations canceled each other out when we added them all together. So the way that we got around that was to square them. So we are going to take the difference of O and E, the observed and the expected, and we're going to square it. And we're going to do that for each color. So what we do is we add those differences squared together. So we sum them together. But before we sum them together, we have to sort of like standardize them by the expected. So our test statistic is the sum of the difference of the O's and E's squared so that everything's positive, divided by the expected. So we'll do this formula for every color, and then we add them up. That's how we find the test statistic. So then when we look at the graph of the chi-square distribution for our problem, our degrees of freedom are going to be k minus 1. So the number of categories you have minus 1. So in this problem, that would be 6 minus 1. So our degrees of freedom would be 5. And our distribution with 5 degrees of freedom would look something like this. So once we find that test statistic, we plot it on our chi-square graph. So maybe that's like right here. And then we find the p-value, which is the area to the right of the test statistic. So this is always going to be a right tail test. So once we find that p-value, we're ready to come to our conclusion. And the conclusion in this hypothesis test is no different than it's been for our previous hypothesis tests. If your p-value is less than your significance level alpha, you're going to reject the null hypothesis. If your p-value is greater than your significance level alpha, then we fail to reject the null hypothesis. Nothing has changed with our conclusions using the p-value method for this type of test. What is a little bit more simple to understand about this test is since our null and our alternative hypotheses will always remain the same in a goodness of fit test, we can word our interpretation the same for whether we reject or fail to reject the null hypothesis. If you are going to reject the null hypothesis, you're rejecting this statement right here that you have a good fit. And if you are going to fail to reject the null hypothesis, then you are not rejecting a good fit. So in other words, a fail to reject conclusion means that the data does fit the claimed distribution, and a rejection of the null hypothesis means that the data does not fit the claimed distribution. So a rejection of the null hypothesis means that the data does not fit the claimed distribution. So you do not have a good fit. But by failing to reject the null hypothesis, you know that the data does fit the claimed distribution. So it is a good fit. Let's go ahead and do a hypothesis test, a goodness of fit test, to illustrate this process. The company who makes M&M's candies claims that each bag contains 24% blue, 13% red, 14% yellow, 16% green, 20% orange, and 14% brown M&Ms. Is this distribution of color correct? Let's test this claim at the 0.05 significance level. So suppose you go out and you buy a standard size package of M&M's candies. There's usually about 56 candies in a package of regular sized M&Ms. So we buy this package of candies, we count that there are 56 candies in the bag, and we separate them by color. I've created a table here for us to organize our information. Once we count each color, we are going to write the quantity for each color under our observed frequency. So here's the counts that we've come up with. 15 blue, 9 red, yellow, we have 6, 10 green, 11 oranges, and 5 browns. So when we add all of these together, we get our total sample size N, which is 56. And remember that K here is 6 because we have 6 colors. So there's a difference between N and K. N is still your sample size, and K represents the number of categories you have. In the next column of our table, I left us a space to go ahead and just rewrite the claimed percentages given to us in the problem. So we know, or we are given, that 24% of all M&Ms should be blue, 13% of all M&Ms should be red, 14% of all M&Ms should be yellow, 16% of M&Ms should be green, 20% are orange, and 13% are brown. So now we want to find the expected frequency or the expected count given those percentages and a sample size of 56. So we observed 15 blue, but if we take any random sample of 56 M&Ms and we claim that 24% of that 56 is going to be blue, what count is that? What is that frequency? So in other words, what is 0.24 or 24% of 56? That's how we get our expected frequency. So 0.24 times 56 is 13.44. So our observed values have to be whole numbers, but our expected counts, our expected frequencies can be decimals. So we expect in any random sample of 56 M&Ms, we expect 13.4 of them to be blue M&Ms. What was our actual count? Our actual count was 15. So we have a little bit more blue M&Ms than we would expect to see, but is 15 considered unusual? I mean, is it close enough to 13.4 in order for it to be considered normal in any package of M&Ms? Probably, but we want to go ahead and repeat this procedure for all the colors, because when we do a goodness of fit test, we're trying to see if all of the categories have the correct number of M&Ms in any random sample of 56. So next, we'll take our 13% red and multiply by 56 to get 7.28. So again, we would expect to see just over 7 M&Ms in any package of 56. We had 9 red M&Ms, which again, not too far off from 7.28. But the point of the goodness of fit test is to measure the statistical significance amongst these observed values here compared to these expected frequencies over here. So we're going to repeat this process for each color, right? And so what we're doing to get the expected count or the expected frequency, E, is we are taking our sample size N and multiplying it by the claimed percentage. So E can always be found by taking the number of items in your sample, which is this N right here, and multiplying it by whatever the claimed percentage is. So next we'll take 14% and multiply by 56. And then we'll take 16% and multiply by 56. 20% times 56. And finally 13% again times 56. So here are all of my expected counts. The one that looks like it's the furthest off to me is the browns. We only counted 5 browns, and we would expect to get over 7 browns. So again, the point of this goodness of fit test is to see if each of these numbers are close enough, the observed and the expecteds. And maybe one like brown, is it too far off for us to say that M&M's company is wrong and they do not fit their claim distribution? Or, is it close enough? So now that we have all the observed and the expecteds, we want to go ahead and calculate our test statistic. So I've rewritten our observed and our expected values on this page. And remember that the formula for our test stat is the sum of the difference of the observed and the expected squared divided by the expected. So we're going to have 6 fractions to add up in this sum. So starting off with blue, our observed was 15 minus the expected, which is 13.44. So we're going to take that difference, we're going to square it, and then we're going to divide by the expected, which is 13.44. Plus, now we'll move on to red. So we'll have 9 minus 7.28 squared divided by the expected, which is 7.28. Plus, now to yellow, 6 minus 7.84 squared divided by 7.84. Plus, now to green, 10, my observed, minus my expected of 8.96 squared divided by 8.96, plus, now to orange, 11 minus 11.2 squared divided by 11.2, and finally brown, 5 minus 7.28 squared divided by 7.28. So we're going to use our calculator to figure out what this sum is. So when I add up all of those fractions, I end up with my chi-square test statistic of 1.8577. So now our job is to plot that on our chi-square distribution. So again, remember our degrees of freedom here are 5. So this distribution is pretty skewed to the right. It's not very normal looking because we have such a small number of degrees of freedom. So if the degrees of freedom are 5, remember the degrees of freedom is also equal to the mean of this distribution, which means that that's right just to the right of the peak. So this is where mu is, just to the right of the peak, right? So now that's going to help us plot where 1.8577 is. So 1.857 is almost 2, but that's pretty far over here, right? This is where our chi-square of 1.86 is, we'll say. And so my p-value is going to be everything to the right of this test statistic. So my p-value is pretty big. Everything I'm coloring in here is my p-value. So I'm going to use technology to calculate this p-value. So I'm going to StatDisk and I'm plugging in 5 degrees of freedom into the chi-square distribution and looking at the area to the right. So I get a p-value of 0.8685. So that's what that shaded in area is. So my conclusion is going to be to compare that p-value against, remember my significance level alpha was 0.05. So my p-value is larger than my significance level. So since my p-value of 0.8685 is bigger than my significance level alpha, and it's quite a bit bigger, right? So this is pretty strong evidence that we should fail to reject the null hypothesis. So now what does it mean to fail to reject the null hypothesis in this problem? So have a look back at your hypotheses. Remember, the null hypothesis was a good fit and the alternative hypothesis is not a good fit. So here are my hypotheses. Remember, the null hypothesis is a good fit and the alternative is not a good fit. So a good fit in this problem means that the distribution of color in M&M's candies is as claimed by the M&M's company. And not a good fit would mean that the distribution of color is different. At least one of the colors does not conform to what they claim. So our conclusion on the previous page was that our p-value was greater than our significance level. So we failed to reject the null hypothesis. So if I'm failing to reject the null hypothesis, I am not rejecting a good fit. So my conclusion is that, or my interpretation is that the observed values do fit the claimed values. In other words, the distribution of color in M&M's candy is as claimed by the M&M's company. So there is sufficient evidence to support the claimed distribution of color in M&M's candies. So in other words, we have the 24% blue, the 13% red, the 14% yellow, etc. So we found that test statistic on the previous page by hand. I wanted to show you what the StatDisk screen looks like when you do this in StatDisk. You can see that in column 1, I went ahead and put my observed counts. And then in column 2, I went ahead and put my expected proportions. This screen right here shows you how once I found that chi-square value by hand, I got my p-value here to the right. But if I go to analysis and I go to goodness of fit test, you can see that not only does it give me my critical value, my test statistic here of 1.86, but it also gives me the p-value. That way I don't have to calculate this test statistic by hand using that long formula. All I have to do is put my observed values here in column 1, my expected proportions or counts here in column 2. And so you can see in this box right here, you want to check whether or not you put your expected as counts or proportions. This problem gave them to us as percentages, so that's why I have the proportions box checked. And then make sure that you tell StatDisk which column you have your observed and your expected. So again, in column 1, I put my observed candy counts. In column 2, I put my expected proportions. I checked the proportions box. It gave me, again, my number of degrees of freedom. It gave my test stat. It gave me my critical value if I was using that method. But the p-value method is what we're primarily going to use. And this is what we used to come to our conclusion of failing to reject the null hypothesis.